Hello, everybody. Let us talk about quantum entanglement. Quantum entanglement is a quantum phenomenon for which Einstein's view was deeply skeptical. And quantum entanglement played a central role in his criticism of quantum mechanics. What quantum mechanics, which was formulated by Niels Bohr and the Copenhagen School. Though Einstein admired the predictive success of quantum mechanics, but strongly doubted its completeness. He believed that the theory was statistical and not fundamental. And Einstein made a very bold statement by saying, God does not play dice. This was his view about This was actually his objection to the randomness built into the quantum formalism. He termed quantum entanglement as a spooky action at a distance. Now, to explain what is quantum entanglement briefly, let us consider two particles, quantum particles, which are prepared in a special correlated state, and that special correlated state is basically, we term it as entangled state. Now what about that correlation or entanglement? That if you measure one's position, that means if you measure one particle's position, you instantly know the other's position. And if you measure one's momentum, you instantly know the other's momentum also. According to quantum mechanics, the second particle's state seems to be known instantaneously, no matter how far the particles are. To Einstein, this suggested that quantum mechanics allowed non local influences, which actually conflicted with relativity's principle that nothing can travel faster than light. And he concluded that the wave function was not full description of reality, but rather a statistical tool, and there must be some hidden variables completing the whole picture. Therefore, he termed quantum entanglement as a spooky action at a distance. I will discuss about the physics of quantum entanglement maybe in my forthcoming lectures, but let us try to understand quantum entanglement with respect to the qubits and quantum computing. So quantum entanglement can be described by using two different equivalent definitions. What is first definition? Definition number 1. It says that given a state of multiple entangled qubits, one cannot express individual qubits separately. That if the state of the multiple entangled qubits is given, but we cannot express the individual qubit states as a tensor product. Now let us say that we are given this is a 2 qubit state. It is ket 0 0 plus ket 1 1 divided by under root 2. So this is an entangled state given. So to this entangled state, we cannot express this state as a linear combination of the tensor product, linear combination of the two individual qubits, or we cannot express the two individual qubits as a tensor product between these two states. So what does it mean? This alpha ket 0 plus beta ket 1 is for the first qubit, and gamma ket 0 plus delta ket 1 is for the second qubit. This is second qubit state. Now, if we try to find out the tensor product between the two, it will come out to be alpha, gamma, ket 0, 0 and the other states. So, we cannot express ket 0, 0 plus ket 1, 1 under root, divided by under root 2 as this linear combination. Now, in contrast to the entangled situation, we have the separable state. Therefore, we have separable qubits. Now, to exemplify the separability, let us consider a state given by ket 0, 0 plus ket 0, 1 divided by under root 2. We can express this 2 qubit state as a tensor product of the individual qubits. How? We can express the first qubit as ket 0. This is cron, this is tensor product symbol, ket 0 plus ket 1 divided by under root. If you take the tensor product of these two terms, you will get ket 0 ket 0 cron ket 0 will give you ket 0, 0 and ket 0 cron ket 1 will give you ket 0, 1, which is this state basically. Now, if you try to compare the coefficients of the states for this separable state, you will find that in this case alpha is 1 because alpha is the coefficient for ket 0, beta coefficient is 0 because there is no ket 1 in the first qubit, gamma is the ket 0 coefficient for second qubit and delta is the ket 1 coefficient for the second qubit. Now, if you find out alpha gamma, so alpha gamma considering from this state is 1 over under root 2. Now, if you multiply alpha and gamma, you will get 1 over under root 2. So, that actually proves that if you try to solve all the combinations, you will find that this is a perfect tensor product between the two individual qubits that give this state. So, this state, this 2 qubit state is a separable state, whereas ket 0, 0 plus ket 1 by under root 2, this is an entangled state. Actually, this is also called Bell state. We will look into what are Bell states. Now, what is the definition 2 of quantum entanglement? Definition 2 says that given a state of multiple entangled qubits, measuring any qubit individually reveals all other qubits. So, if you measure one qubit only, it reveals the status of all other qubits. That's what I was trying to explain when I was trying to discuss the physics part of quantum entanglement. So, you come to know the all other individual qubits also, the state of all other individual qubits also. Now, let us consider this state. Before measurement, the probability that first qubit is 0 is half and the probability that first qubit is 1 is also half. So, some probability values persist for the second qubit also. Now, before measurement, both the qubits are in superposition and let us say we measure first qubit. The first qubit can be ket 0 or ket 1. If the first qubit is ket 1, then we can say that the second qubit is also ket 1 from this entangled state. So, what we can say that if the first qubit is 1, we can say that the second qubit is also 1. If the first qubit is 0, the second qubit, this is without measurement. Second qubit we are not measuring, first qubit we are measuring. If we measure the first qubit and we say that it is 1, we will come to know that the second qubit is also 1 without measurement. If the first qubit is 0, the second qubit will also be 0 and that too without measurement. This is the case when we measure the first qubit first, and there can be second case if we measure the second qubit first, and that combination of if the second qubit is 1, if you measure it, then without measurement we can tell that the first qubit is 1, and similarly for 0. This is known as quantum entanglement, and this is because of quantum entanglement that we need not to measure the second qubit, and because the two qubits are entangled, if we measure one qubit, we will be able to tell about the qubit state for the second qubit. Now, even the first and the second qubits are thousands of miles apart. Even then, we can tell the state of the second qubit. Now, this is known as quantum entanglement. In contrast to entangled qubits, we have separable qubits. That is, measuring one qubit will not reveal the state of the second qubit. This statement is basically for separable qubits. Now, in the concept of quantum entanglement comes very important concept of Bell states, and which are also known as the EPR states. EPR stands actually for the name of the three scientists, Einstein, Podolsky and Rosen. So these are four Bell states. These are considered to be entangled states, and these four Bell states are ket 5 plus, given by ket 00 plus ket 1 divided by under root 2, which we just mentioned previously also, and it is also denoted by ket B subscript 00. Bell state for 1 0 is also known as ket 5 minus, and the state is ket 00 minus ket 1 divided by under root 2. Then there is ket psi plus and ket psi minus, and these are the states. So these four states are actually Bell states, and these are entangled states, and this entangled state is formed using two qubits. And these four Bell states, we also term these four Bell states as Bell bases. So this can be a basis set, ket 5 plus, ket 5 minus, ket psi plus, ket psi minus. Now the question is that how can we generate this 2-qubit entangled state? Now, very simple circuit, quantum circuit is there to generate the Bell states. The circuit involves one Hadamard gate, which we will apply to one of the qubits, and then we apply the C0 gate. Now, if you divide the quantum circuit in terms of ket psi 1, ket psi 2 and ket psi 3, and if we apply ket 0 and ket 1 to the inputs, what Bell state we will achieve? Let us try to understand how this quantum circuit works actually. So we are applying ket I as ket 0 and ket j as ket 1. So therefore, ket psi 1 is basically the tensor product of ket 0 and ket 1. So we can express the tensor product as ket 0 1. Now, ket psi 2, if you want to know about ket psi 2, basically it involves the Hadamard gate acting on qubit I. So ket 0, so Hadamard will be applied to ket 0 and ket 1 remains as it is. So once you take the tensor product, you will get ket 0 1 plus ket 1 1 divided by under root 2. Then there is the C0 gate. C0 gate is if ket I is 0, no change in the ket j state. If ket I is 1, then this state will be ket j will be flipped. So in this case, to the first 2-bit combination, the I state is 0, so no change in the overall state, so it remains ket 0 1. But in the second 2-qubit combination, ket I is 1 actually, so therefore the second qubit will flip and you get this state, which is equal to ket psi plus. So this is a Bell state. Depending on the input that you apply here, you can generate all the 4 Bell states using this simple circuit of Hadamard gate and C0 gate. Now similarly, we can generate the Bell states for all the other Bell states also. Now let us take a numerical example in which we are given ket omega as a quantum state, ket 0 1 minus ket 1 0 divided by under root 2, and we want to find out that ket omega is entangled or separable. So we have to actually prove this. We will prove this by contradiction, and let us assume that ket omega is not entangled. If it is not entangled, so therefore we can express this ket omega or this 2-qubit state as a tensor product of the 2 individual qubits. And this can be done like this. This alpha ket 0 plus beta ket 1 for the first qubit, gamma ket 0 plus delta ket 1 for the second qubit, and the tensor product of the 2 qubits. We can express this quantum state. So if you take the tensor product, you will get this alpha gamma combinations and so on. And if you try to compare the left hand side and the right hand side, you will find that alpha gamma is equal to 0 because there is no coefficient, there is no ket 0, 0 state on the left hand side. So therefore alpha gamma will be equal to 0, beta delta will also be equal to 0, and alpha delta is 1 by under root 2, beta gamma is 1 by under root 2. Now from here, we know if you look at this state, if you look at this alpha delta and beta gamma, you can very well say that because alpha delta has got 1 over under root 2 value, so even not alpha and not delta can be 0. So delta cannot be 0 here and beta cannot be 0 here, right? But if you look beta delta case, it is equal to 0. So this says that either beta is 0 or delta is 0. But from here we find out neither beta is 0 nor delta is 0. So therefore our assumption is wrong, that we assume that this ket omega state is a separable state, which proves wrong by contradiction, and we can safely say that ket omega is an entangled state. So Bell states represent entangled qubit pairs. These are also referred to as EPR pairs. Once you have the Bell states, it is possible to get the original input back. Right, to do this, we have again a very simple circuit. We have to actually reverse the circuit. So how you do the reversal of the circuit? In the generation state, you have Hadamard gate, and after Hadamard gate you apply the C0 gate. But what you do in the reversal, you apply the C0 gate first, and you take the adjoint of the C0 gate, and you then apply the Hadamard gate, and again take the adjoint. Now we know that the adjoint of H is equal to H and C0 adjoint is equal to C0. So this is actually this circuit, and if you use this circuit, you can recover back the input from the Bell states. So this was all about quantum entanglement related to 2 qubits, and in general we can apply the concept to multiple qubits and quantum computing. Thank you very much.